So welcome everyone. Tonight, the topic is extraterrestrial environments. This was something that Sally suggested last week. Not quite this title. She was just talking about exoplanets and the environments of exoplanets. And so I reshaped the title to make it more clickbaity for YouTube. So extraterrestrial environments is tonight's topic. But as usual, first we'll do the news. Okay, the James Webb Space Telescope has completed its first multi-instrument alignment. Now that doesn't mean it's aligned all the instruments because it's still working on MIRI, but it's aligned 3 of the 4 instruments, including, not including MIRI, which would be the 4th one, to the mirror alignment it had for the NIRCam. And apparently, the NIRCam alignment was sufficient for the other 2 instruments, which one of them is heavily spectroscopic. So I think it bodes well for future spectroscopic images from the Webb. They're waiting on the cool down of MIRI before they start. They're waiting on the completion of the cool down of MIRI before they start doing the alignment on it. So there was another SpaceX launch this week, Transporter 4. This is one of their commercial rideshare programs where they launched a bunch of satellites off of one rocket. Since the launch and orbit would be towards the south, they literally had no radio coverage as they were deploying the satellites. They're going to have to come back and get the camera imagery later from the upper stage. So you got to watch the launch. You got to watch them stick another landing with the first stage. You got to watch the fairings separate, and that was it. But they did leave everything on running so you could watch the success or failure of it all the way until they completed the deployments. And they did. So if you remember last week, we talked about the SLS, the Artemis 1, being rolled out to the launch pad at the Cape. And the fact that it was there meant that the crewed launch of SpaceX to the International Space Station had to be delayed a couple of days. It turns out it wasn't shared use of the pad itself. It was shared use of the fuel and oxidizer tanks and plumbing between the 2 pads. So if this gets to be a problem, especially once the larger SpaceX launches are taking place from the Cape, I think that SpaceX may want to invest in having their own tanks and plumbing. But we shall see. By the way, I didn't check on the status. This afternoon, Artemis 1 should have completed its wet dress rehearsal. The definition of the wet dress rehearsal is they roll the rocket out to the launch pad. They connect it up to everything from the pad to the rocket. They fill it all up with its fuel and oxidizer, and then it sits there on the pad the normal amount of time such that it might have launched. And it gets to within 10 seconds of firing its main engines, and then they shut down the launch process, drain all the stuff out of the rocket, and then roll it back into the vehicle assembly building. So that's what they call a wet dress rehearsal. And the U.S. astronaut has returned safely from the International Space Station aboard the Soyuz capsule with 2 Russian cosmonauts. The Russian cosmonaut that was the commander of the space station turned authority over to one of the U.S. astronauts. And I think at this point, there are no cosmonauts aboard the ISS.
Didn't they say today that they weren't going to allow any more Americans up there?
I did not see that. Because they do currently have 2 scheduled SpaceX flights to the International Space Station carrying NASA astronauts.
I don't think that's going to be a go.
I'm not sure what's stopping it because they're not flying on a Soyuz. I'll look into it. So last week, there were 2 solar flares, 2 eruptions from the sun that headed towards Earth. And apparently one of them that started out later had more velocity behind it than the first one. And so they caught up and merged but rather than saying they merged, they described it as one of them cannibalized the other. There's clickbait for you. Cannibalizing solar flares. But apparently it was strong enough that on Wednesday you could see the aurora from Colorado. It's not the lowest the aurora has ever been as far as latitude goes, but it certainly was a wide view of the aurora. It wasn't a nice ribbon definitive aurora. It was just giant swaths of color. Okay, and until this afternoon, I got a better picture of this. I couldn't quite understand what they were talking about when I was watching it on the videos. The Hubble Space Telescope, not to be, publicly overshadowed by the James Webb Space Telescope, released, hey, we found the farthest, oldest star that we've ever discovered. And they've already named it Arendelle. Anyway, they spotted it using gravitational lensing. And you wouldn't normally capture this, but when you saw it on the videos, this particular picture was squeezed down into lower resolution where it looked like this line pointing at the star actually pointed here, not here. So it was just squeezed down. And I thought, well, that seems rather unusual that you would have a star that's a blue or blue-white star that you could still pick up that far away in deep space, that many billions of light years away, and it would still be blue. Shouldn't it be shifted to red, or maybe into infrared, or maybe even into radio if it's really that old? And then I got this picture from NASA that was, I guess, less zoomed up and cropped. So Arendelle is this red star right here. The next question I had was, in the gravitational lensing, they said mirrored star cluster, and they've got one cluster here and one cluster here. Star clusters usually hang out on the outside edges of galaxies. If this is the galaxy it's hanging out on, there's a lot of stars in there that we're not seeing as separate stars. Why would we see a star this old of this type as separate from its galaxy, when we can see star clusters, which are many thousands of stars represented by just a smeared blob? So I'll have to research this further and find out, how do you know it's an individual star? And if it's really that far away and that old, how come you're seeing it in the visible red range as opposed to deep infrared or radio? Questions to be asked. And I posted the video from last week on the YouTube site. I did something different. I actually dug down and said, I've looked at some other videos and they have these time markers along their timeline. So you could see the text there. And as you move from one section to another, you'll notice that the text changes. So introduction, news, and then presentation. And you can see the time markers.
Yeah, nice.
There's a little tiny gap right there between them. And then there's another one down here where it switches from the presentation to open topic discussion, which actually took several times as long as the actual presentation. That's even after I edited it. So I found out how you define those. When you're defining the description, you literally just throw in some text. It looks like timestamps followed by text on separate lines. But the first one has to be 000. It can be 0:0:0, or it can be 00:00:00, which is what I chose to use, so they all line up. But you throw those into the description without any kind of formatting around it, and YouTube pulls that out and says, oh, you mean the time index markers. And it actually hyperlinks them. So if you click on them, you can actually click on them and it'll take you to that part of the video.
Oh, that's a great idea.
Wait for a second.
Great idea.
So it's not something that I created, but there is no YouTube like learning session that gives you a hint how to do this. I had to go find somebody on YouTube that did a video that says, hey, here's how I do my timeline markers. So I said, well, I can learn from him. And then I watched 2 other videos explaining it better or worse. And so I said, well, I got the idea for it now. Think about it for a moment. If YouTube did not have this capability and they wanted to add it, they could do it one of 2 ways. They could put in like new buttons to like edit video or create timeline or something like that, where you could actually put the data in. But instead they chose to magically decode it from the ad hoc text of the description. And there's pluses and minuses to that. The plus is I can now go back and edit the description text of all the prior videos to put in the time markers. I don't have to like recapture the video or reload the video. And the time markers are not actually in the video. They're completely separate from the video content, and it's just how YouTube presents it. So learn something new every day.
Yeah. That's 365 things a year.
You said pluses and minuses. What are the minuses?
The minuses are, if I wanted to pull this data out of here, if I wanted to look across, 10,000 YouTube videos and find out what all their time marker values are, I cannot access an object that purely has that data in it. I have to replicate exactly what YouTube does to parse the ad hoc text to find the time markers. So it's, when I work in computer software, you never want to be pulling data from ad hoc text, because you have to create too many protective measures of somebody just put that phrase in there. Somebody just put some zeros in there, and you're not really sure of what you're decoding. So that's why you typically object associate, or in medical devices, it's something called semantic interoperability, where the data is actually defined or defines itself as what it is. So that's the pluses and minuses of it. This is not really great for open interoperability, because you have to parrot the ad hoc text parsing of YouTube. And if YouTube ever changes it, you have to change your stuff too.
Oh.
So I'll look to doing these on future ones, and I'll probably take the videos that have had the most views, like our James Webb Space Telescope video, which is now somewhat over 1,000 views. And I'll put in time markers for it so people can jump straight to the presentation or straight to the discussion if they want to.
Good idea.
And also in the category of good ideas, ever since I formed this group, I've wanted for us to have a place we could go if we wanted to do an observing session. The Broward County libraries are no longer doing their observing sessions because they all close at 6 p.m., which is typically before sunset. And Fern Forest Nature Center, it looks like they're not going to have their observing sessions in the summertime months because of too much clouds and rain. I guess they didn't want to do the indoor presentation stuff. So they're on the decline. And we're not getting any requests. Probably post-pandemic recovery is still taking effect from other places like city parks or businesses. So I'd like to have a regular place we can go to if we want to do some observing for a particular celestial event. And here's where Markham Park is. Now, this is current light pollution information from March 19th. I could go further than March 19th. They actually have images all the way up to April 2nd, but there were clouds, as you could tell by all the rain this afternoon. So all it got was just the map outline and no actual nighttime light information. So this is as of March 19th of this year. There's Markham Park. Now you know why it's so light polluted, because the light extends from the city of Sunrise and up from Weston all the way beyond Markham Park. But there's a place out here which is nowhere near as bright that Helen and I will be going to tomorrow night to see what it's like. It actually has public access up until 11:59 p.m. Might as well say midnight, but they open at 12:01 a.m. and close at 11:59 p.m. So they literally have a couple of minutes of actual closure per day. I think it's probably some business issue or staff assignment issue that requires them to officially be closed for a certain amount of minutes per day. Anyway, we'll go take a look there. This is a place that Broward County recently spent several $1 million renovating. And for those people that are into monitoring, there's no such thing as climate change involving sea level rise. They took the public areas of this spot and they raised them all 2 feet because during heavier rains or high, king tide periods, the area was underwater. So they spent your tax dollars to raise the public areas of this site by 2 feet, not 6 feet. Don't want to be excessive here. Don't want to make it obvious. 2 feet. So we'll take a look at that tomorrow night. And are there any other news items I might have missed? Any comments before we get started? Okay, hearing nothing, let me switch it over. So tonight's presentation is Extraterrestrial Environments, kind of a clickbaity type of topic, but we're going to discuss exoplanets, their environments, and how compatible or incompatible human beings are with them. So it's probably more parameters associated with exoplanets than most people have ever heard of. But I tried to bring up every one of them that might be something we want to pay attention to. So in this case, the humans are the extraterrestrials. Given some future where we have the technology for doing so, we're going to be visiting exoplanets and evaluating whether or not it's a place that we can live, we can visit, we can maybe send probes to. What's the old saying? It's a nice place. I don't mind visiting there, but I wouldn't want to live there, that kind of thing. So we're the extraterrestrials, and I'm not postulating any non-humanoid types like grays or lizard people or frozen oceans with fish people. No blue humanoids like you'd see on a certain sci-fi TV show. And
Andorians?
No, not Andorians. I was thinking of Orville. And no floating cloud blob creatures like Carl Sagan suggested. First, let's start where we can live. There are places on Earth where humans thrive. More than just survive, it's places where we come together and we live in large quantities. More than survivable, in fact, it's comfortable. Hawaii, South Florida, San Diego, places where people go because the environment is conducive to not only your existence, but your comfort. Then there are places on Earth where humans can exist, but with precautions. Like it's a very hot place. So, you don't go outside much in the daytime when it's sunny, very dry. Like, we can visit Death Valley. No problem visiting there. You have to just wear the right clothing and avoid maybe the sun at certain angles. Very cold, Mount Pleasant, Mount Weather, those kind of things. Mount Weather, very windy. But people do activities there, scientific research, monitoring, those kind of things. You just have to wear protective clothing whenever you go outside. And your preference is most likely to stay inside of a protective structure than it is to go outside and just hang around. And then there are places on Earth where it's not possible for humans to exist without bringing their own environment. So any place where it's excessively windy, hot, cold, underwater, high pressure undersea, low pressure at high altitudes, toxic gases near volcanic events. Helen and I know about that from Yellowstone. Or Chernobyl, highly radioactive sites. You typically, if you're going to be there for any amount of time, you have to create an environment that prevents you from dying while you're there. If you want to go outside in those kind of environments, you have to wear anything from just clothing to environmental suits to, sealed ambient environments where the gases can't get in and poison you, all the way to having a shielded structure because there's radiation. And then we have the familiar ones where we bring along our own protective environment. It's called a submarine. You can go really, really deep, deeper than the human body would tolerate, but you can go down there. You can go to the bottom of the Marianas Trench, and you can be down there for a while and then come back up. But you don't go outside your submarine, your bathyscaphe. So once we leave the surface of the Earth and go out into space, there's no air for us to breathe. The temperatures are too extreme. The radiation and micrometeoroid particles might kill us. So we wear spacesuits whenever we go outside. Otherwise, we wouldn't survive. And when we're not outside in our spacesuits, we must stay inside of our spacecraft, which creates a human-compatible and artificial protective environment, so we can hang out more comfortably in shirt sleeves, so to speak, rather than wearing a spacesuit full time. And then there are places that are just beyond the limit of human tolerance. We can't create sufficient technology to protect ourselves, so we send robotic probes there. So think of the surface of Venus. Between the temperature, the pressure, and the acidic gases, even the probes that have been sent to Venus only last for less than days before they're destroyed. So our best technology doesn't survive. There are places that have high particulate densities. Think about Venus and Io. They have volcanoes. The ash and dust from the volcanoes are corrosive. They can destroy things. Mars sandstorms. We lost 2 rovers to Mars sandstorms because they got covered in sand and dust such that their solar panels wouldn't work and their batteries got cold and they stopped working. And if you remember from a few weeks ago, the diamond rain, theoretically, that falls on Neptune. Not something, if we think hail on Earth is bad, imagine diamonds falling from the sky. Not good. And then there's the radiation fields of Jupiter. When we sent the unmanned Juno spacecraft to Jupiter, we didn't think it was going to last very long. It wasn't all that shielded. So there was concern for radiation fields. And the Parker Solar Probe actually has a radiation shield because not only the radiation, but the temperature would be such that it would melt the probe. So they had to come up with this plate they could put in front of the probe that would take the brunt of the radiation and the heat from the sun. There's also the cold, high-pressure atmospheres where we can't exist and we don't have technology for it, like Saturn, Uranus, and Neptune. We actually burned up the Cassini space probe by ditching it into the atmosphere of Saturn. Then there's all those multi-100-mile-per-hour high winds that we have on Jupiter, Saturn, Uranus, and Neptune. We just don't have anything that can take that. No structures, no craft. And then there's, if you wanted to get a space probe closer to the sun than the Parker Solar Probe, we just don't have the technology to deal with that. And certainly if you wanted to do something like, I want to go sample directly inside the plasma of the sun, not going to happen. So with the best environments we can create, they're borderline, so humans can only survive for limited periods of time before stuff starts breaking down. And the more incompatible or unsustainable an environment, the shorter the survival period. So we have a lot of exoplanets. If you remember, I stated there's now 5,000 and counting exoplanets that we found, and we're still looking for more. Initially, we looked for exoplanets through telescopes that were Earth-based, and we were looking for minute wobbles of stars, sort of the Olympic shot put. Yeah, not shot put. Yeah, hammer throw. Hammer throw's the right one. Yes, hammer throw athletes, where as they swing the weight around them, the athlete sort of wobbles in the center of rotation as the weight goes around. We found we could detect very large planets around other stars by monitoring the wobble. It's a minute wobble. It's like fraction of a pixel this way, fraction of a pixel that way. We then went to examining the light that we receive from stars. And as the light dips, so the light curve dips, we say, well, that's because something went in front of the star. And based upon the amount of dip, we're judging how big it might be. But it could also be how far away it might be. So we use this method predominantly for judging exoplanets these days. And two noteworthy space probes that do this are Kepler, which did 2 missions, and the TESS space probe, which is, I guess you could call it the successor to Kepler. It can look in more places at larger areas of sky, but still we're only talking about a few handfuls of patches of sky. And then somebody got clever and said, you know, if we're evaluating the light coming off that star, and then when it dips, we know that's because the planet, the exoplanet, went in front of it. It gives us not only a different amplitude for the light, different brightness for the light, it also gives us a slightly different color. We can use that color spectroscopically. So we take the color of the star that we're viewing when the exoplanet goes in front of it, and we subtract from that the color of the star when the exoplanet is not going in front of it. And the colors that are left can be split in a spectroscope and now tells you the atmospheric chemical composition of the exoplanet. So we're progressing the use of instruments we already have. And the James Webb Space Telescope actually has multiple spectroscopic instruments on board where they're going to do that very thing. But there are stars that are too bright, as in they're so bright that when their planet goes by, there's not a big enough dip for us to notice. Or the star can be, near a red or a brown dwarf, and the planet is so small going around it, or it's tidally locked on the backside of it, that we can't see any exoplanets. But most of the places that we've looked for exoplanets, we found exoplanets, and more than just one. You usually find a small handful of them. And then there are the places where the equatorial plane of that solar system is not in line with that of Earth. Think of it as, okay, when we look at the sombrero, it's an edge-on galaxy. So we can't judge brightness of stars in that galaxy. The pinwheel galaxy, that's very nice because it's flat to us. So that's just pointing out that not only is space large and three-dimensional, but not everything is in the orbital plane that aligns with us such that we can see it directly. So if a solar system was actually tilted up 90 degrees and the planet was orbiting this way, there would never be any dimming of the star. When you can't find an exoplanet, there may be another reason other than that star has no exoplanets. But maybe someday we'll find other means of detecting exoplanets. I don't know, gravity wave detection or something. But think about it this way. We understand the James Webb Space Telescope and its multiple hexagonal mirror segments, but they're all connected together. Imagine if we flew up a couple of hundred individual smaller mirrors, and they flew in kind of a formation, and then you adjusted them all individually. They're not connected together. So you'd take your image and then you would post-process it as to the phasing of which mirror is closer to the secondary. So once NASA gets tired with building one-piece telescopes where there may be parts, but it's still just one instrument, and you start building dispersed instruments, we may find that we can image exoplanets directly, but not yet. So how many quantities? And like I said, we've got Kepler and TESS that we're looking in small parts of the sky, and they found, 3 to 6 planets, some having more per star. And not only that, but we've improved our Hubble Space Telescope observations through software and through optical instrument changes and larger telescopes on the ground, as well as software. We are now finding more exoplanets from ground-based observatories. High altitude, but still ground-based. But not every exoplanet should be considered easily human habitable. We have a narrow range that we can exist in. So just as initially when we were doing the first Kepler mission, we did not look to anything other than yellow stars. We didn't broaden our minds, so to speak. And we were only thinking of a narrow Goldilocks zone. We weren't thinking to maybe if we go a little farther, either colder or hotter, we could still have a habitat that we can exist in, but it's not truly comfortable. There's no shirt sleeve weather, so to speak. And we're finding that out on Mars. Mars is far colder than the Earth. The atmospheric pressure is lower, but we're now thinking of, putting human habitats on Mars. So that's well beyond our ability to be comfortable. We have to have spacesuits and habitats and provide oxygen and heat and electricity from solar generation or radioisotope thermoelectric generators, but we can still exist there, and we can exist in quantity, in structures. So we're broadening things out. We're going to stop looking just where the light is shining the best. What are the variations of exoplanets? So not all exoplanets are the same. There's a lot of variety in them. We're now starting to think of, well, we're going to start looking at the atmospheres of them. And once we do that, it adds a number of parameters that we need to get right to make it comfy for humans, or tolerable for humans, or survivable for humans. So the first thing we encounter is, what is the size of this exoplanet? Well, they can range from asteroids too small for us to see to planets that are several times the size of the Earth. But when they get too big, we have to worry about, and what's the gravity like? We don't want to go there and wind up being just in a puddle. And then the composition of their atmospheres. Is it toxic to us? Will it melt things or corrode things? The surface, will we sink through it? Is it like solid that we can stand on? Or is it liquid or somewhere in between, kind of like quicksand? And then what's the core of that planet? Is it a gaseous core, a solid core? And does it have a rotating metallic core so it has a magnetic field, which would be good for keeping radiation out? What's the surface activity of it? Does it have oceans? And if it has oceans, oceans of what? Is it water? Is it methane? Nitrogen? What is the ocean? And if it has storms, storms of what? Is it storms of water? Is it storms of methane, nitrogen, hail, rain? Does it have volcanoes? If it has volcanoes, what's coming out of the volcanoes? Is it ice? Is it water? Is it rock? Methane? So we have to think about what the surface activity is to determine whether or not it's survivable. And not all orbits are circular. So if an exoplanet has a highly elliptical orbit, it may pass by its sun and bake itself, and then it may go far out from its sun and freeze its atmosphere. We believe that a couple of the Kuiper belt objects in our own solar system, when they get towards the far end of their somewhat elliptical orbit, their atmosphere gets so cold that the atmosphere freezes and falls down to the surface of the planet for years. So if you went to live there and all of a sudden the planet moved a little closer to its sun, and what you thought you were standing on and put your habitat on suddenly became vaporous and went away, it would be a bad day. Then what about the rotation of the exoplanet? You want the planet to be equally heat bathed by its parent star. You don't want it to be tidally locked so that there's always a cook or freeze scenario. And then the distance of the exoplanet from its star will vary whether or not you cook or whether or not you get irradiated. So if we had to judge, what are we looking for? What's good real estate for us to pick out? The star heat and radiation varies with the star temperature and the age of the star as to its stability. The composition of extrasolar planets, are they gas or terrestrial? The size of them, are they Earth size, Jovian size, somewhere in between? Are they at a correct habitable distance from their star? What about the parent star and the relationship of the exoplanet? It can be orbiting and rotating, or it can be stationary in its orbit about its star, like a geosynchronous exoplanet kind of thing. It would be geosynchronous, it would be extrasolar synchronous orbit. It can be rotating or not rotating. It can be tidally locked. The duration of its year could vary based upon whether it's closer or farther from its star and how fast it's orbiting it. If you have too short a year, that's a problem. If you have too long a year, that's a different problem. So what are the variances we can work from based upon Earth as our only known example? So Earth is tilted on its axis to allow for seasons and for atmospheric convection. That's a good thing. Our year duration is sufficiently long to allow for seasonal agriculture. Either that or animal and plant life has accommodated itself to the actual duration that we currently have. We do know that some crops can grow in shorter seasons based upon the latitude where they're planted. The day duration needs to be sufficiently long for reasonable work-sleep periods. There are psychological issues on Earth when polar regions undergo 6 months of cold nights and nil daytime. So you don't want to have too much dark for too long or too much daytime for too long, because people's gets nuts.
SAD.
And if you think about it, the definition of the Goldilocks zone, Earth is not actually in the center of the Goldilocks zone for our sun. It's closer to being Venus, but then Venus is a hellscape, so we're the next best place. And you don't get to choose, you're just there if it's your parent star. So we need a dense enough atmospheric pressure to retain gas, water vapor, and to protect us against micrometeoroid debris hitting the planet. And the atmosphere needs to be sufficiently dense to allow for aerodynamic transportation, or airplanes and jets and prop jobs and stuff like that. And we found recently that, hey, that even works on Mars. Even though it's thinner, we can adapt the aircraft to fly in those environments. But at some point, there's going to be a threshold where the atmospheric pressure is too low. I don't know about it being too high. That might actually be easier. But you want to monitor the gravity. The particulate densities need to be low worldwide, not high for long or excessively harmful. What this comes out down to is, if you think it's bad during pollen season, imagine if that was on Mars and you had glass-like grains of rocky material that, should you breathe them, it would be kind of like getting asbestos in your lungs. So you want to make sure the particulate densities are sufficiently low for your survival, or you have to wear something to protect you from it. And that if it's not glass, maybe it's, acidic things like on Venus. So you want to make sure the particulate densities are low and survivable. And strangely enough, you want to make sure that the ionizing radiation, in other words, you have a strong enough magnetic field to keep out the bad stuff from the sun, but not so repressive a magnetic field that, radio only works in a narrow band and everything else is just noise from the sky. And the gravity needs to be sufficient to not lose your atmosphere in order for you to have time to broaden your civilization. But the atmospheric, the gravity cannot be so strong that it disallows space travel. There's a piece of software called the Kerbal Space Program where you can adjust the parameters of your space flight. And if you increase the gravity to, let's say, about 3 Gs or more, the normal baseline gravity, we don't have any rocket technology that would allow you to leave your planet. So think about that one for a moment. Hey, we found an exoplanet. It seems to have the right environment for human life. How come they've never visited us? They haven't discovered the technology that would allow them to leave given their higher gravity. And we need to have a sufficient electromagnetic shield to protect us against debris and radiation from the parent star. It needs to have an abundant source of liquid water, whether we decompose it from chemicals or make it from chemicals, for use in agriculture and chemistry. Water is used to grow crops. Water is also used in a lot of chemistry and chemical and manufacturing processes. So we need an abundance of water. But even though we have water, we need to have an abundance of large, dry, connected land masses for agriculture, to put dwellings on it, and so we can, move around from one place to another. Transportation. Although we could use sailing ships, I guess. They're slow though. And we need a wind speed that is sufficiently low in those large areas of flat, dry ground for effective agriculture. And if you remember in the history of the Midwest of the US, there were Dust Bowl times when it was so dry and so windy that your crops wouldn't survive because it would blow away the topsoil and all you had left is kind of Sahara sand. And you need to have an element variety rich environment of ground for agriculture, chemistry, and advanced technology. You have to be able to grow your crops in something. It can't be potatoes from human manure all the time. And you have to have certain elements available to you for you to grow out your manufacturing and your technology. It'd be nice to have some iron in the ground to make things, steel. It'd be nice to have some maybe lithium so you can make batteries. Lots of chemicals needed in the ground. And it would be nice if the planet's not too big and it has a large natural satellite like Earth's moon to keep the medium-sized exoplanet from wobbling, because that would throw chaos into your weather patterns. So there's a sliding scale of habitable exoplanets. A human survivable exoplanet, given the right structures and suits and conditions and stuff, it doesn't need to be a perfect duplicate of Earth. So when people say, we're looking for Earth 2.0, Earth 2.0 does not need to be an exact clone of Earth 1.0. It can have some slight variations and still be survivable. Think of all the places where people live and, people from other parts of the Earth would go, I'd never want to live there. It's too hot, or it's too cold, or it's too inaccessible, or too remote, or whatever. But people do live there. The day can be somewhat shorter or longer. It doesn't have to be, 24 hours, which is our day, not exactly. We're a little less than 24 hours, but it works. The rotation duration needs to be balanced with the diameter. If you have a small diameter planet and it's rotating too fast, you don't want to have to nail things down. Reminds me of that Twilight Zone episode with Burgess Meredith, who suggested maybe the Earth should stop rotating, and everything flew away. The gravity can be a little more, a little less. It shouldn't be crushing, but it shouldn't be so light that if you live there for a while, all your muscles atrophy and you can't get back to Earth. Its year can be somewhat longer or shorter, but we need some reasonable duration for a growing season to grow crops so we can have agriculture and survive. The night can be darker, it can have fewer lights in the sky, and if it's not developed, doesn't have a lot of industry, then it will have a darker sky. The daytime can be a little brighter. We can wear UV protective clothing and glasses and hats and stuff, so that's a little better, but not too bright. You want to be able to have enough lights in the right color so you can see, but not so much that you cook. And speaking of seeing, it'd be preferable if the daylight was in the visible range, not too much into the infrared where our eyes don't work, and not too much into the UV where our eyes don't work and can be harmed. So you don't have to walk around outside all the time with night vision goggles or wearing leaded sunglasses. The particulate densities need to be limited and come to pretty much zero every so often. If you remember the old Flash Gordon movie, we don't want to have hot hail. The electromagnetic field can be a little more, a little less. We need protection from the solar radiation. We need to still be able to do radio, and we don't want a magnetic field that's so strong it sucks the iron from our blood. And, the atmosphere can have a tolerable level of radio interference, just like we do here on Earth. We don't need access to all radio bands. The higher frequencies will be fine, though. The tilt of the planet on its axis does not need to be vertical. It can be a little off. We don't want it on its side because we'd like to have the poles get some starlight. so we could use more of the planet. It doesn't need to have a moon, but it needs to be substantially wobble free. So it can either just be a little larger and have, more substantial mass. It needs to have an abundance of water, plus an abundance of dry land. We need something to drink, something for industry. But we don't want, Kevin Costner's water world. The dry land, it'd be nice if it had rolling plains, as in, large areas of flat land where we can do agriculture, put up big manufacturing facilities. So, dry land that's all mountainous is not really that great. And you want the wind speed to be tolerable, especially over the large plains. I spelled plains wrong there, Plains. Over the large, flat, dry areas for agriculture. So I was trying to find a way, much like the Goldilocks zone, to say what would be the habitable zone. So I created down the left a series of parameters and the not really Earth-specific values, but Earth-tolerable values. In other words, it's not the average values for these based upon the average values on Earth, and it's not even really the extreme values from Earth. It's what I judge to be the tolerable values on Earth. So if you think about, if you're in Phoenix, Arizona, and it's in the hot part of the summertime, if the air temperature gets above 112 degrees Fahrenheit, airplanes don't fly. But you could take it to 120 degrees and people could still probably survive it. So that's why I said, well, average temperature, minus 20. Minus 4 degrees Fahrenheit. Lots of people live in colder environments than that. 122 degrees Fahrenheit or 50 degrees centigrade. There are times when, Death Valley might be a little warmer than that, but those are tolerable limits. So I went through the entire list of parameters and said, what would be kind of like the minimum, maximum tolerable values? And then I said, if you take every one of those parameters and you put it across a 1 to 100 spread, and then you overlap those, what you would get is, in the center, a habitable zone. So that would be where it's not bad. You might have to wear some comfortable clothing. If it gets a little worse, protective clothing, get to environmental suits or spacesuits. And as you move out to the edges, you start having things to be not habitable, but tolerable. Or not tolerable, but yeah, we could, bring our own environment or build our own defensive structures to protect us from it. And then once you get out to the edges, where it's not enough of whatever the parameter is, or too much of whatever the parameter is, I deem that as insufficient long-term supply or indefensible as there's too much of it. So that's what it came down to, is the habitable zone, kind of like the Goldilocks zone with a lot more tolerance to it, and not just temperature, it's all the other things. So are there any other parameters that people could think of that we need to make sure stay within a certain range in order for people to either survive comfortably or with, environmental protection or bring their own supply?
Well, I was thinking about the development of geothermal power, and I was wondering about what would the core of the planet have to be?
Well, we know the core of the planet needs to be preferably molten metal or compressed elemental metallic gases, such that it has an electromagnetic field to keep out the bad solar radiation and to create a defensive field against radiation particles.
Yeah.
But as to whether the core needs to be hot, I think you'd find that if you have a molten core, or if you have a gaseous core that is producing a metallic magnetic effect, it's probably going to be hot. And you don't want to be drilling down all the way to that level. So if you have, let's say, tectonic plate activity, that's going to give you lava, and that's going to give you heat. So you do have a source of thermal energy beneath the ground. So that's a good point.
Right.
you do need a source of electricity, and most people would just go, you've got solar, you've got plutonium decay for thermoelectric, that should be fine. But if you have a planet around a red dwarf star at the appropriate distance so as not to get bathed by radiation, then
Yes. Yeah.
the sun might, that star may not be compatible with photoelectric cells.
Yeah,
Yeah.
but
I have a few more factors you could consider, Monroe.
Go ahead.
Dangerous weather. You can't have too frequent tornadoes or hurricanes, things like that. You have to have some sunlight. You can't have constant rain or constant lightning. Tectonic activity, earthquakes, volcanoes. You can't have too much of that. And dangerous life forms that already exist on the planet. We can't move to a planet full of T-Rexes.
Or plants that have thorns that shoot you in the chest and
Exactly.
change your personality.
Yes.
Or giant Venus flytraps that can consume you. Yes, those are all.
Way too much Star Trek, someone.
Did I say Star Trek?
And Little Shop of Horrors.
Little Shop of Horrors, yes. Helen, have you seen Little Shop of Horrors?
I think I watched it in Portuguese.
Steve
I need
Martin?
to watch in English again.
Yeah, the Steve Martin version's the best. So, any more parameters that we can think of being listed? I think we've come up with some good ones, some beyond what I had thought of. Okay, so in conclusion, human beings can survive on a wide range of Earth environments without special protection. There are people that live in Alaska and eventually get to the point where it's only 40 degrees. I'm walking around in my shirt sleeves and short pants. Person from Florida would go, oh, that's just way too cold. I need to bundle up. Providing that we have protective clothing and structures, we can even take that to a farther limit, assuming the atmosphere is not too extreme. And if we do have the appropriate clothing and structures, we can survive for even longer periods of time in less hospitable environments. But the amount of time we can survive in the less hospitable environments is a matter of how inhospitable is it? Do we just need to have structures and suits and bring our own atmosphere and lead line things, or is it just way too much for any extended period of human habitation? If so, we'll send the robots, the autonomous robots, to the rescue. Things like Juno, Perseverance, those, Parker Solar Probe, those go out places where people can't, and they do the science for us. So exoplanets can have environments that are anything from human tolerable to human protective to human extreme, and even beyond the limits. We can send our probes. Humans are creative and resourceful. I wouldn't rule anything out. I would just say you need to be wise of these things and go where you can go, and where you cannot go, make sure you're protected. So anything else? Hearing nothing, that's all I have.
well done, well done.
And I'm sorry for about the lack of pictures, but I do have a few links. There's a couple of NASA websites that have articles on telling you about exoplanets. So if you want to see that the Earth is unusual, as in it's habitable for us here, but elsewhere it's less habitable. But then my thought was, maybe we just evolved to fit here. Maybe if it's an exoplanet that's less hospitable, if there's life there and it's sentient, intelligent life that grows a technology and a society, and they could evolve to match their environment. Even on Earth, there are places where the atmospheric pressure is lower than it is at sea level, and people develop larger chest cavities and bigger lungs. Just that's their genetics. Well, you could go to an
Yeah.
exoplanet that's a little bit of a stretch for humans where they might survive just fine going, I don't see what the problem is. And
Yeah,
then
2
there's,
billion years ago, we couldn't breathe in this planet. If we
Yeah.
visit a planet like ours, if only like 3 billion years old, you cannot breathe. That is not enough oxygen being produced, it's still in the oceans.
yes, we had to have the firstborn critters come in and suck in all the bad air and poop out all the oxygen so we can breathe. So then the next one was, how do we make a planet habitable? That's pretty much the presentation that I gave. They didn't get anywhere near to the level of detail that I did as to the factors.
Oh,
They just talked about, you have to be a certain distance from your star and you have to make sure you can breathe and the basic stuff. And then for
Yes,
those
I
people
get-
that are curious about the Kepler Space Telescope and the TESS probe, some information regarding those. And then the NASA video on 5,000 exoplanets and counting.
Is there
Because-
one that kind of looks favorable at all?
So far, the only thing that they've looked at is, are they the right distance from their star such that if they did have water, would the temperature be such that it would be liquid? Not the atmospheric pressure, not whether there's a magnetic field to keep you from being irradiated. And they've even looked at, well, even if the planet is rotationally locked to its star, there might be a terminator zone, a line around the planet that's habitable. Even if one side is too cold and one side is too hot, there may be a temperate zone that you could survive in. But I think it's more a matter of, let's figure out how to go faster first. Then we can take all the data from all these exoplanets and say, let's go there first and see how it really is. And then we can figure out whether we want to stay there or not. But the James Webb Space Telescope is going to be doing spectroscopic imaging of the atmospheres of exoplanets so they can determine, is there water? Maybe not how much there is, but is there water? So, you were going to say?
I was going to say, you're saying to go faster because right now, from what I just heard this last week, there isn't any exoplanet that we have the ability to get to at this point.
Oh, we have the ability to send a probe to it, but you might have to wait a few thousand years before it gets there.
That's what I mean. They said that no human to get there.
Well, you could if you built a generational ship like the students in Weston proposed, the aerospace equivalent, the rocket equivalent of Kon-Tiki, where you have a multi-generational ship. You're born on Earth, you jump on board the ship, and you have enough of everything to survive for multiple generations. So even
Okay,
if you're
do
not,
we have the capability to do that now? Because according to them, even doing that isn't really even available for us to do now. We don't have the ability to do that. At least this article or podcast I listened to was saying that is one reason why they're having a hard time funding more things for it, because a lot of people are starting to say, we can't get there. We have no means to get there. So I don't know. Do we?
I think that's one of those hurdles where as long as we can say, we'll never conquer it, then anybody that tries will go, fat lot of luck. You're going to have conquering that because nobody ever has. And if they spend a lot of money doing it, then they can say, we told you wouldn't be successful. So I had a whole presentation on, we create hurdles to make sure we can't accomplish something. Someday we'll get smarter than that and go, okay, so why don't we do a Manhattan Project kind of thing for warp drive?
Or let's go like a Manhattan Project for energy.
But that's not going to make any difference whatsoever on whether or not we can successfully get to another star for science purposes. We need more than energy. We actually need.
I think if we resolve the problem of energy, we can improve, the efficiency of Earth domes that we did before, because most of the problem is that the energy generating those close, those enclosures, that they have like the deficit of energy, and you start having with air pumps and oxygen, and the astronauts, they are testing the devices and the plants. They are using a lot of energy just to keep up with the thing. So that's, so far they tried like 2 or 3 times and never worked, because we always have a deficit of energy. So I think the first step that we have is to develop independence of energy that's useful for science and is useful for the problems that we are facing right now at this moment.
Why can't we do more than one? Why can't we
Exactly.
work on energy and work on propulsion? Why is it just
Sure,
one
that's
thing?
no problem.
Yeah, but we have to have the will to do it. And I think the best way to create the will to do it is to entice corporations that want billions of dollars to do the research in these areas, but they would rather do research that is in within reach technology. They don't mind building the next generation of stealthy aircraft for billions of dollars, because they know they can kind of do that. And then they can, build the next one after that and the next one after that. But if they truly solve the energy problem, they would take all the future revenue off the table.
Yeah, but
That's-
it's just the mentality, the American mentality, that you have to involve corporations. You have to remember that the biggest innovations that went distributed for the whole country, it was initiative of the government that then, when established that science, when established that technology, hand out that to the industry to actually charge for that, like they did. And many things, the internet, the roads, the telephone, the communication systems, so like everything, it was first developed by the investment of the government and then handed out to the industry.
Not quite. All those big projects that we did, the government created the money and gave it to the military and the industry partners to do it. If you said, well, the Manhattan Project, the military could build the camps, the structures, but the military can't create wood. They're not loggers. So they had to get the wood for the buildings from corporations. They had to get the plumbing and the electrical. They could install it, but they had to get the materials from corporations. So anytime we have large government projects, you have to involve the private sector, and that enriches the private sector corporations to the tune of billions. The interstate highway system, courtesy of President Eisenhower, that was a great way for road construction companies and cement providers and steel providers to make a lot of money over the entire of the United States for many decades. But it was the government that created the money, created the initiative to do it. So I think it's merely a matter of, if we really want to accomplish, getting beyond these handful of hurdles, we have to entice the government, to entice corporations to do what we need them to do, to assist us, to assist the government in conquering these hurdles. I'm sure that there had to have been some high-level, serious talks within Florida Power and Light next era to say, should we build any more fuel-powered electrical plants? Because they just spent close to $1 billion in Florida transitioning them from fuel oil burning to natural gas burning. And then the price of natural gas went up. They don't like it when the price goes up and then they have to go back to the Public Service Commission and ask for a rate hike. They would much rather have the rate hike be because they built infrastructure. Well, as they transition from natural gas plants to solar photovoltaic, that leaves a lot of money on the table, as in, what are you going to say? The sun wasn't hot enough, so we need a rate hike? We have to go put out some more solar panels, so we need a rate hike? You can't just arbitrarily charge more money per kilowatt hour just because you want to make more money. So that leaves a lot of money on the table. Whereas if you said, my plant is powered by fuel oil and the price of fuel oil goes up, you can say, well, it went up by 5 cents, so I better raise the rates by 7 cents. There's margin in that. So you're leaving that margin concept on the table when you start running your power generation through renewables. But FP&O made the decision, and they're now producing more power via photovoltaic cells than the grid can consume. So they're shoving that power to the rest of the Florida grid to consume it. And once again, they're producing too much. So they put in batteries. And once again, they're producing too much, but they're still growing the amount of photovoltaic cells within the Everglades of Florida. So the next step is we'll take 500 megawatts per day, and we'll use that for electrolysis of nearby water to produce hydrogen, and then we'll store the hydrogen and we'll convert the turbines that burn natural gas to also be able to burn hydrogen. So they can be even more self-sufficient of their fuel and basically create money rather than ditching it to the ground. So yeah, you have to have a solution that the companies themselves realize they can't draw it out anymore. They have to make the transition. And I think that if the Earth was threatened by something, and it has to be something that's decades away and catastrophic, extinction level event, we'd find how quickly we would come up with multiple Manhattan projects, regardless of how many billions it takes for us to survive. But luckily, none of that is needed right now. All we need is will. Okay, enough of my soapbox. So I have a topic for next week's discussion, which is basically what's inside of a telescope mount and how it works. I'm not going to get down to the source code level of the programming, but I was recently tearing down my Ioptron mini tower to get it working again, and I learned a lot of stuff in the process. It's working once again. It was as simple as cleaning built-up oil and grease off the optical encoder disk of one of the two drive mechanisms. Sounds complicated, but it was literally just some alcohol on a rag, on a paper towel, and then wiping down a plastic disc that had little black notches in it. So I'm now tearing down my IEQ45 Ioptron mount to solve a problem that it has with occasionally stopping in the declination or altitude drive. And I'm learning a lot about the internal design of that. So I put all that knowledge together in a presentation and thought that might be something, maybe not for our audience to be too enthused about, but I think it would be a good video to have out there on the site, for the public to take a look at.
Take pictures.
Yes. People like pictures.
And how to fix stuff too.
Well, yeah, but because I actually sent an email off to the Ioptron mini tower user group and asked them what could the problem be, and nobody could come back with a clue after almost a week. And I said, well, I guess I'm gonna have to diagnose this thing myself. And then when I found out what it was, there were actually people that were encountering the same symptoms, and they went, oh, that makes sense. And they went off and started fixing their own mounts based upon the information that I handed to them on a platter. So I'm now doing the same thing for the other mount, which is, has anybody got a pinout for this particular internal cable? The old saying, there's no user serviceable parts inside comes to mind. But that's just a cable that nobody knows what those wires do. They know there's 6 wires in the cable. They know that it's a pH 2.0 type connector system, but maybe there's some power in there, but is the power continuous or is it pulsed when needed? And what are the other wires for? What kind of signaling? I got to figure those things out. So I'm breaking down the mount.
And we might have some video or some pictures from our outing tomorrow.
Yeah, I was thinking about that. Do we want to make 2 trips there, 1 trip in the daytime for good pictures, and then go back out there after dinner to, get nighttime image?
Yes, we can do that.
Okay. So I might pick you up earlier. I'll let you know.
You have an
Sounds
idea what
wonderful.
time?
What was that?
Do you
It
have
sounds good.
any idea what time?
Probably 4:30, something like that.
Perfect.
Yeah.
Anybody
it-
wants to come in?
Let's make it a nice round 4:30.
Where are you going?
Everglades Holiday Park.
Thank you.
It's at the western terminus of Griffin Road at US 27. I'm going to pick Helen up at 4:30. It'll probably take us 40 minutes to get there. So round about 5-ish, we'll be there for the daytime, walking around and picture taking. And then we're going to go away to the Chipotle that's in Weston, and have something to eat, and then go back there probably around 9 o'clock at night, after astronomical twilight, so it's reasonably dark, and see how many floodlights they have for the swamp boats.
And figure out if they can turn off that if we do some kind of event.
I think that would be talking to the park manager. I'm not going to set up an appointment with him ahead of time, but I found that the park manager for Markham Park is also the park manager for Everglades Holiday Park. And Sarah, who was the naturalist at Markham, is also the naturalist at Everglades Holiday Park. So it'll be people that know us, know Helen and myself, that
Know that you are paying.
well, know that amateur astronomers are not, a threat to society, and we're going to bring out things that look like giant missile launchers that aren't.
Yes.
And then we need a place to be dark, and we need some flat ground to set up telescopes. So
And place to go to PP.
yes, well, that's the other thing is Broward County spent several $1 million renovating Everglades Holiday Park, and I'm sure that there's lovely new ADA compliant bathrooms there.
There are two things that we should film, like the bathrooms. Of course, not creepy filming, just showing
I know
the
what you
facility,
mean. I
how
know what you
clean
mean.
and how nice they are, and
Hey.
like both sides to put in the video.
Given the fact that they run airboat operations out of there, it wouldn't even surprise me to find they have showers.
Oh, that's fancy.
Yeah. But we also want to see, I know they've got a gift shop. They've got a brand new gift shop, which I would think is enclosed. The old gift shop was sort of enclosed. It had screen doors and screen windows. My guess is the new gift shop is all fully enclosed and air conditioned to better sell things. But I want to see if they have some kind of meeting room or administrative room. If you know, Markham Park in their admin building actually has a meeting room. And we've actually held meetings in there when the observatory was under construction and renovation.
Oh, can you remember before you leave the house for me to pack the light meter, or you have one?
I'll remind you to pack yours.
Okay.
I have one, but it's network connected. It's not handheld.
Oh yeah, mine is handheld.
I know. And make sure the battery's good.
I could never even change the batteries. It's like enclosed and you have to have like special screws, and I never did.
I don't know that the screws are all that special. I think it's a 9-volt rectangular battery on a clip. So you probably have to undo 1 or 2 screws.
It's still working.
Okay.
So that will be a nice place for us to actually visit and do events, and maybe, do some kind of star party if it's dark enough, and if we have like a nice area.
It should be definitely darker than Markham Park. It might be as dark as Markham Park used to be 8 to 10 years ago. But it's all a matter of what kind of lighting they put in for the nighttime airboat events, because the park is open until midnight or 11:59. Is there anything before I stop recording? Okay, stopping recording.